And now we take a look at a much more fun problem. Let's say we have a 1 liter, we have 1 liters of a solution of 250 molar sodium dihydrogen phosphate and 0.3 molar sodium hydrogen phosphate. It's important when we have complex acids like this, we have to understand what HA and A minus are. Remember that these are kind of, anytime we're talking about conjugate pairs, they always differ by 1 proton. And so our HA in this case is going to be H2PO4 minus. That's okay. We choose what HA is and what A minus are. The only distinction is that they have to differ by 1 proton. That's it. So A minus is going to be our other our other component of the solution here. And if we're going to be using the Henderson-Hasselbalch equation, it's important that we use the Ka for whatever we assign Ha to be. So if Ha is dihydrogen phosphate, we're really looking at Ka2 for phosphoric acid, which I have looked up for us, 6.3 times 10 to the negative 8, or if you take the pKa of that, it's 7.21. That's the one that we use. You always use the Ka or the pKa for Henderson-Hasselbalch for whatever you decide Ha to be. Remember, Ha, we kind of just write it as neutral, but it doesn't have to be. Ha could be H3O+. Doesn't matter. Or it could be NH4+. Doesn't have to be neutral, doesn't have to be whatever. The only difference is A minus has to have 1 less proton than Ha. So as long as you get those right, always use your Ka for your Ha species, the protonated form. So, with those kind of things in mind, here's the question now. What is the pH after adding 0.2 liters of 0.1 molar NaOH? Now we have volumes to worry about. And we want to think about moles. So, thankfully, because we have 1 liter to begin with, that means originally, we have 0.25 mole of our HA and 0.300, if I remember correctly, yes, mole of our conjugate base. And we're going to be adding 0.2 liters of 0.1 molar NaOH, which means we are adding 0.02 moles of NaOH, right? Moles is moles per liter. So our molarity is moles per liter, so the moles of NaOH would be that molarity, 0.1, times the liters, or divided by the liters, 0.2. So we're going to be doing that, times, because you know what I'm saying. The molarity times the volume is the moles. There we go. So we have that much moles of NaOH. So in this case, we know it's going to react fully with our HA, because this is a strong base we're adding. It's going to react with the strongest acid. The strongest acid is always the one that has the more protons for a pair like this. So we know overall 0.2 moles of OH minus are going to neutralize the same amount of moles of dihydrogen phosphate. So we can write out the chemical equation, and we're going to get our HPO4 2 minus and some water. We're really going to ignore the water that comes out here. It's going to be a very minor amount. 0.02 moles of water is 0.36 grams, so 0.3 milliliters. We're going to ignore it, thankfully. So we can use an initial delta F table here, not really an ice table because this isn't an equilibrium. This is a straightforward reaction. Weak acid plus strong base is a forward reaction. There's no equilibrium happening here. We have our 0.25 molar to start, 0.02 moles, We're going to subtract our 0.02 moles. Again, we want to get rid of all that extra base that we're adding. We're going to be having our 0.300, and we don't really care about the water, so forget it, plus 0.020. With these, you should never have any coefficients, thankfully, so we don't have to worry about that. But we end up with 0.23 moles, no new moles of OH minus, and then 0.32 moles here. And then the only thing we have to worry about is that when we're doing our Henderson-Hasselbalch equation, we need concentrations. And in the easy problem, we kind of ignored the volume change. But if we're mixing solutions, there's always going to be some volume added, right? So we now have our total volume of solution is going to be our initial volume, 1 liter, plus our plus our added volume, which will be 0.2 liters. So the new total volume is 1.2 liters. And so we have to recalculate our concentrations based off this new volume. So the concentration of dihydrogen phosphate is 0.23 over 1.2, which will be 0.23 divided by 1.2, and that's 0.192 molar. And for the other side, we have our HPO4 minus. We have 0.320 moles over 1.2 liters, which is 0.267 molar. So both of these have actually gone down because we have a bigger volume than we had before. And so when we're going to do this, we should go ahead and now plug these into our equation. So pH equals pKa plus log of A minus over HA. And in doing so, we can go ahead and see we have our pKa is 7.21. 7.21 plus the log of A minus. We have to remember which one we set as A minus. That's the one that has more negatives, right? So 0.267 over 0.192. And we simply need to plug this into our calculator. So 7.21 plus log 0.267 divided by 0.192, close parentheses, and we get 7.35. So same calculation. We just had to do a little bit more work with dealing with the volume. And so we can do it this way by actually doing all the calculations. So hooray! All right, now to ruin everything. Since both your A minus and HA were divided by the same number, you can mathematically work that out elsewhere. And you'll find that you can actually just plug in the moles directly. So all that for nothing. But the point is we did another lovely example of our Henderson-Hasselbalch equation. And so we were able to see this in action again. So I'll just prove it to you now. If we take our original numbers, 0.23 divided by 0.32, and then we have to divide the whole thing by our new volume, we will get our answer. So, all right.